I was starting to wonder, like,
Yeah.
did I not get the memo? Is it canceled today?
I'm sorry to do this to you, but I gotta use one of my homework passes.
It's okay.
But don't you have most of it done? I mean,
I know. I just didn't get it done. I stayed up
Yeah,
to
but how many do you have done?
like 4-ish.
Yeah, we'll save it just in case, because
Okay.
there are like 8 problems, so like 4 out of 8.
Yeah.
And then homework is worth 20% of the grade, and that's one assignment out of how many?
Yeah.
You're looking at, 0.5% of that.
Okay.
Oh.
good morning, Aiden and Ian. Well, I should probably cancel that. It's not so loud.
Ooh, steamy hot water. Ooh, that is really steamy. I shouldn't open that. I can get up to 70, like, it washes at really high temperatures, like 70 degrees Celsius. Okay, everybody. How are you, Ava? How are your other, you have other AP classes, right?
Yeah,
How are they going?
well, I'm a week behind in every class.
Are they going super fast?
AP Stats is, but that's because he's like trying to like finish early. Which is fine. I've been preoccupied. AP Literature isn't that bad. It's just writing essays over and over again. This time consuming.
That sounds horrible. That's everybody's different. I didn't hate writing, but I wasn't like super pumped about it either.
Am I like allowed to drink in class?
No,
No?
unfortunately, sips of water. And wait a minute. Yeah, you're not supposed to eat or drink in class. Sorry.
Morning.
Good morning, Jackson. Oh, who should we call on today? List the 7 strong acids.
Oh, I
Kira.
think you should. Really? Okay, Kira.
I have one question.
No, that's
Sorry.
me.
Is it time to start? No.
Yes, in the cats class.
You've never noticed that before.
Oh, no, it goes down. This is a small year, 18 students in AP Chem.
Isn't it always small though?
Well, it depends on how small. Usually in the 20s. This year was 18. Next year's, yeah, there are 28 students signed up for AP Chem, which is big.
Do you know any names?
No, I don't know the names. They don't tell us lists until later, but I'm kind of like, how many people are gonna drop is what I wonder,
Oh, wow.
once they realize how tough this class is. Also considering like how little chemistry we taught this year.
Oh, yeah, I can imagine.
But, it is what it is. I mean, how would you guys feel if I went faster in this class?
I have a stroke, I think.
Well, that's why I just kind of decided like there's just no possible way for us to get through everything. All right, let's go through the homework. We got a few more problems to go over. But before we start, we are gonna call on, let's see, random generator here. Oh, all right, Luis, tell us the seven.
Hydrochloric acid, nitric acid, sulfuric acid. Can you hear me?
People on Zoom can. I'm not sure if he can though.
We can't hear you if you're talking, Mr. Strauss.
Hear me. Whoop. There you go. All right. That's better, right? All right. So thank you, Luis, for telling us those 7 strong acids, which all you have memorized by now. All right. So let's go through the rest of those homework problems because they're all humdingers. Oh, gotta start at chapter 14. Yep, give me a second here. All right. So let's see. We still have to do. All right, let's start off with 61. How could you prepare 1600 mils of a pH of 1.5 solution using concentrated 12 molar HCl? All right, so this is, again, I would say a practical stoichiometry problem that if you were in a lab, you would be asked to do to prepare this. So first of all, you want to find out what is the concentration that you need. Well, pH is negative log concentration of H plus, right? And so if my pH is 1.50, that means, so I'm going to take the inverse log. Oops, I don't think I'm supposed to say that. Doesn't Mr. Guy get upset if you say inverse log? Or is it anti-log? I think I'm supposed to say anti-log. I'm afraid to ask Mr. Guy because he'll give me a disapproving look if I say it the wrong way. So all right, so what I get is 0.0316 molar. All right. So on your calculator where it says log, you gotta do the anti-log. I think that's the correct terminology, anti-log. Yeah, 10 to the x. It's the opposite of the log, the anti-log. So that's what I get as my molarity, 0.0316 molar. So that's what I need is the concentration. Now, how much of it do I need? I need 1600 mils. So convert milliliters to liters. And for every 1 liter, I'm going to need 0.0136 moles of HCl. And when you buy hydrochloric acid from the company, the chemical company, it comes as a concentrated 12 molar solution. So there are 12 moles of HCl in 1 liter. So when I multiply that out, I get 0.00421 liters, or 4.21 milliliters of 12 molar HCl. Okay. Now, when you mix a solution up, you probably know this, or maybe you've heard this, you always add acid to water. Okay. So you would have your container, you fill it with your water first, then you're going to add the 4.21 milliliters of acid. So you add acid to water. A&W root beer, acid to water. That's just a way to remember it. A&W, acid to water. Or the other kind of silly saying is, do as you oughta, add acid to water. All right. So the reason why that is if you do it the other way around, if you have the acid in here first, and then you add water, a strange reaction can occur where it heats up the acid really fast, and then the acid jumps out of the beaker. And I've seen this happen twice in my life, once to someone in chem lab, and once actually to me. At the end of a Friday, I dumped some acid into a sink, and it hit the water in the sink and it jumped back out. So, except that was the correct way of doing it, acid to water. But yeah, it's really weird to see. Like, it was like when I saw it in college, it was like a cartoon, you know, where they throw the water out of the bucket and the water turns around and comes back at you. It's like you dump the water in the sink and it just jumped right back out into his face. It was just the most bizarre thing. All right. So now we have to do, is it 73? What was the other problem? 69 or 73 or both? Oh. Nathan, do we have to do 69? My records say yes. Okay. I might do this one a little bit quicker because it's kind of the same as number 67. It's just extra practice. All right, so we've got this acid. Now that's a lot to write. So remember we'll write just HA, so we don't have to write out the big old thing. So we're trying to find the pH of a 1 molar solution. So make our ice table because it's a weak acid. My initial concentration is 0.1 molar. Zero of this, zero of this. I'm going to shift right, shift right, shift right. My equilibrium expression will be x squared over 0.1 minus x. And then what my Ka, they give me the Ka is 1.35 times 10 to the negative third. Yeah, I don't think I'm going to actually solve this one out because I think we got to use the quadratic equation. Because look at this compared to this. Is it more than 100? Kind of right on the border. So I'll just solve it assuming maybe I'm wrong. So what you can do is still assume it's too small and solve for x. Another 0.01116. And then what they call the 5% rule. So is this number greater than 5% of your initial molarity? You read about that in the book, right, Jackson? I was actually asking during, but that's okay. So 0.0116 divided by 0.1, what does that get me? Why am I using a calculator? I should be able to do that in my head. So that comes out to be 11.6. So is this a valid assumption that X is too small? No. So that means we'd have to go back and do this with the quadratic equation, okay? So I'm not gonna do that though, because that's gonna take too much time. All right, 73. I should put the chat room up so you can see something. All right, calculate the percent dissociation in the following solution. So let's write the equation. Then we're gonna have to solve to our ice table. And 5, 0, 0 minus x plus x plus x. 0.5 minus x, x. The Ka for acetic acid, I believe, is 1.3 times 10 to the negative 7th.
For 73.
For acetic acid, yes, 73.
It's like 1.8 times 10 to the negative 5 is what they.
Oh, yes. There we go. 1.8 times 10 to the negative 5th. So x squared over 0.5 minus x. All right. So this, yeah, what I do wrong?
You didn't do anything wrong.
Oh. All right. So this number and this number are off by more than 100. So this time we know for sure that this x is too small. So 1.8 negative 5th times 0.5 square root. All right, so that's the molarity of 8 plus at equilibrium. So how much of that broke apart? .6% dissociation. Okay. All right. Any questions on that homework before we continue to complicate things? Boy, yeah. All right. Let's take a look at a special strong acid, and that is sulfuric. Okay. So these are like special cases, but they come up so often that we need to go through them. Okay. Crystal Lake. No, you guys aren't allowed to eat or drink in class. I am. All right, so strong acids break apart 100%. But the thing that's unique about sulfuric acid, it's only the first hydrogen is strong. Okay, so all the other strong acids are monoprotic. One hydrogen comes off of it. HCl, one hydrogen there. If you look at all the strong acids, only sulfuric acid has got a 2 there. But it's only the first hydrogen that's a strong acid. The second hydrogen is a weak acid. Therefore, it's a double arrow. I'm gonna write it the other way so that H's are. All right. All right, so the first hydrogen is strong, the second hydrogen is weak. All right. So suppose I asked, what is the concentration of all species in a, let's keep it simple, 0.100 molar solution of H2SO4. Okay, what is the concentration of all the species in H2SO4? Just kidding. Well, I guess we got no choice. Oh, no, it's okay. That's fine. Yeah, let's do it. All right. So the Ka for the second deprotonation is 1.2 times 10 to the negative second. Okay. Stremel, do you still teach math? Do you still teach math? Can I ask you a math question?
Now I don't have to know the answer.
I'm just curious. When you take the opposite of the log, is it called the inverse log or the anti-log? Isn't it anti-log? Or does it matter?
I think I heard it called both, actually.
Because I thought one of them is wrong. Like this, I thought like saying the inverse log was like actually technically not the way to say it, but anti-log.
Anti-log sounds better.
Okay, we'll go with anti-log. All right. We had it from the expert right here, Mr. Strumlow.
Anti-log.
The anti-log. All right. So how much H plus is going to be made from the second reaction? How much H plus is going to be generated? It's a weak acid, right? So thinking about that, Tyler, are we going to get a lot of H plus from H plus from the second deprotonation? No, it'll be insignificant. So in calculating the concentration of H plus, we can just look at the first deprotonation, okay? So if this is 0.1 molar, it's a before and after table because it's a strong acid. So before 0 and 0, after I'll have 0 of this, 0.1 molar of this, 0.10 molar of that. All right. So I know right away that there'll be 0 of that. And I know that the concentration of H plus will be that. Okay. So we don't care at all about the second reaction. It's not going to generate enough H plus to change it, okay? Now we're going to then look at, because the problem, I want to know the concentration for all the species. All right. So initially, it's a weak acid, so we have to do an ice table. So my initial concentration is 0.100 molar, right? And this is where, if there's a little twist to the problem, this is it. What's my initial concentration of H plus? Point 100 molar, right? Because we got that H plus from the strong acid portion. We've got no sulfate, no SO4. So as long as there's a 0 there, we know which direction it's going to shift, right? Correct? Because there's 0 sulfate, we know then here it's going to shift to the right. So at equilibrium, we're going to have this. My Ka is now going to be 0.1 plus x times x, or 0.1 minus x, and the Ka is 1.3 times 10 to the negative second. So the math is not exactly super fun, but we can do one of these like that. You'll see my concentration there is 0.1, and this is to the negative second. So the x is going to be significantly big. We cannot assume it's too small. So we have to work the algebra out. So I'm going to distribute the top first. I think I did that right. All right, combine like terms. Point 1 minus 1.2 times 10 to the negative second. Oh no, it should be adding. Okay. Now we're going to have to put in the quadratic equation, negative b plus or minus b squared minus 4ac all over 2a. So let's do this real quick. So I got X to equal 0.0095. Hopefully I did that right. Did I do that right, Lucia?
I think so.
So then we go back up here, and at equilibrium, my sulfate is going to be 0.0095 molar. And my this is going to be 0.1095 molar. And this is going to be probably should have left that up at 0.0905 molar. Okay, so we now know the concentrations of everything. All right. So the concentration of H plus is that. So if I'm going to try to find pH, okay. Now, like I said, every single problem is unique. Okay, so remember in the beginning, I said that the amount of H plus being produced in the second reaction is insignificant. I was wrong. The concentration I picked, 0.1 molar, because I just picked the concentration out of the top of my head, that yielded 0.100 molar. The second deprotonation yielded enough H plus to give me that total concentration of H plus. So the amount of H plus was not insignificant. So my pH then is based off of, sorry, it's 0.10, right? So that's the number I'm using to find my pH, not that. Now, if my concentration was super big, like suppose I did a 10 molar solution instead of 0.1 molar. If I did a 10 molar solution to start, if that was 10 molar, then when I was doing my ice table, this concentration would be more than 100 off. So then the second hydrogen wouldn't matter. So this is where, like I said, this stuff it's tricky because you can't just say, oh, that's what you always do. You have to think about, okay, what's my is it strong or weak? What's my concentration? And then does the autoionization of water matter? You know, in this case, the problem it doesn't, but other problems it might. All right, Ari, that problem was so much fun. Let's do another. So again, keep in mind, sulfuric acid is special because the first proton is strong, the second one is not. All right, here we go. Make sure you're using pencil when we do this problem. Let's do it for a triprotic weak acid, phosphoric. This is a common one. It's in sodas. It's in a lot of foods as a preservative. You guys ready and hold? You excited, Ian? All right. So let's start off. Let's do a 0.1 molar solution, okay? Nah, let's do a 1 molar solution. And I'm sure I'm going to use the quadratic equation. All right, so what's going to happen with this? Right? It's a weak acid, so we have to do an ice table. Here's my initial concentration. 0 of this, 0 of this. I'm going to lose X of this, gain X of this, gain X of this. All right. So then this is the first proton coming off, so we call it Ka1, the first dissociation. All right. You good with that so far? Now, the second proton is going to come off, right? So what is my initial concentration of HPO4? I'm sorry, H2PO4. The initial concentration of it is X. What is the initial concentration of H plus? X. How much of this do I have? Nothing. So that means I'm going to lose Y of this, gain Y of this, gain Y of that. So then my concentration equilibrium is going to be X minus Y. That's plus Y and Y. Just remember, this was an elective. You chose this course. And then that's going to deprotonate. Wait, I forgot to write the expression. My fault. I'll write this expression. Second Ka is equal to H plus over HPO4 all over H2PO4 1 minus. All right. All right, so then the next reaction, HPO4, oh, I want to do it in black. HPO4 is going to deprotonate, make H plus and PO4 3 minus. To our ice table. You giving up, Deering? All right, so what is my initial concentration of HPO4, also known as biphosphate? So my initial concentration, I go up here. That's my initial concentration. Why? What's my initial concentration of H plus? X plus Y. I have 0 phosphate. So my reaction is going to shift to the right. So I'm going to lose Z. And I'm going to gain Z. So at equilibrium, I'm going to have Y minus Z, X plus Y plus Z, Z. My third Ka, Ka3, it's supposed to be a 2 minus there. All right, Luis, you ready to do some math? Matrix, take the blue pill. All right, so let's plug in some numbers here. So H plus is X plus Y plus Z. PO4 is Z. This is over Y minus Z. But now here's something to keep in mind. Actually, not keep in mind. This is the correct way to do this. The way we wrote this stuff down, it seems sequential. Like, okay, first this happens. The first hydrogen comes off. Then second, this happens. The second hydrogen comes off. And then third, this happens. The third hydrogen comes off. Okay. Yeah, it's sort of. Remember, all 3 of those reactions are happening at once. Okay. We end up with one equilibrium concentration for everything. So if the equilibrium concentration for hydrogen is this, right? That's the equilibrium concentration for hydrogen. Then that's the equilibrium concentration of hydrogen for all the reactions. Because you can't have 3 different equilibrium concentrations for hydrogen. It can't be X plus Y plus Z, and at the same time be X plus Y, and at the same time be X. You can only have one equilibrium concentration. So that means we got to change these to be X plus Y plus Z, and change this to be X plus Y plus Z. And that means that this guy has to be Y minus Z. And it also means that this one up here has to be, oops, didn't mean to do that. If that's the equilibrium concentration X minus Y, then this one up here must also be X minus Y. So now we actually have the correct expressions. And now you're like, oh my gosh, I'm gonna give up. Don't give up, because we can approximate. Let's write down the Ka values. So the Ka3 is 4.8 times 10 to the negative 13. Ka2 is 6.2 times 10 to the negative 8. And Ka1 is 7.5 times 10 to the negative 3rd. Hang in there, guys. It's going to be okay. We're going to get through this. All right, look at my Kas. That's to the negative 3rd. What happens in the second one? Negative 8. What's the difference, rough or take? It's about to the negative 5th, about 10,000. So whatever is generated in the second reaction is 10,000, a factor of 10,000 times smaller. What's generated in the second reaction is insignificant. So we're not going to have to worry about what happens in the second reaction. Same thing down here. Compare the third deprotonation to our first one. Times 10 to the negative 13th compared to negative 3rd. A negative 10, that's over 1 billion times smaller. Okay. So if you lost $1 billion, Pent, it ain't going to matter if you lost an extra dollar. All right. So basically, we can say that these guys are too small. Okay, they're too small to matter. So that's going to make it a lot easier. So let's go through and then actually solve everything out. All right, so I got X times X over 0.1 minus X equal to 7 point, no, it's not 0.1, it's 1. Sorry, just kidding, 1. Okay. Now I picked my concentration this time around to be 1. So that in comparison to my exponent, we can be assured that that X is too small. Okay. So I did that on purpose so that when I solve for X, I can do it without the quadratic equation. My X is 0.0866 molar. So what that means is that this is my concentration of H plus for all 3 reactions. All right. And this is my concentration of H2PO4. All right. And what is my equilibrium concentration here? 0.10 molar, because we said X is too small to matter. Okay, so I have now 3 of my equilibrium concentrations. So when I go down to this problem down here, the second one, I know my equilibrium concentration for that already. It's 0.0866. The fact that I'm getting some extra H plus is insignificant, okay? It's always the case with with diprotic and triprotic weak acids, okay? Sulfuric acid was a different case because the first proton was strong, okay? But for weak acids, you never have to worry about the second or third proton, okay? Your pH is going to be based off of that first proton, okay? So that's why I know my concentration of H plus. Down here, 0.0866 minus Z. No. I erased the wrong one. Just kidding. This one. I was looking at the wrong. This is H2PO4. It's this one. It's the wrong one. The fact that it's losing Y, the Y is too small. So I get 0.866 molar times Y over 0.866 minus Y. That Z is too small, so we don't care about that Z. That Y is too small, so we don't care about that Y either. So that means that Y disappears. So guess what Y equals? So now I know the equilibrium concentration for my HPO4. Then we go down to here. This is my equilibrium concentration, 6.2 times 10 to the negative 8th. My equilibrium concentration for the H plus is 0.0866 molar. The only thing we don't know is Z. So at equilibrium, I have 0.0866 molar of that. Z of that, 6.2 times 10 to the negative 8th molar of that. And my Ka is 4.8 times 10 to the negative 13th. So now we can solve for Z.
Chapter 14 test.
Good question. The question is, are we having a chapter 14 test? I've been thinking about that. I don't know. So we now know the concentrations of everything. The sulfate is phosphate, just kidding. Is 3.43 times 10 to the negative 19th molar. The concentration of HPO4 is 6.2 times 10 to the negative 8th molar. The concentration of H2PO4 is 0.0866 molar. The concentration of H3PO4, I don't need parentheses for that one, is 1 molar. And the equilibrium concentration of H plus is that. Yes, but it's insignificant. It's, it's below the 5% rule. So your mathematicians would have loved to have done a matrice. Your chemist says, close enough. So if you want to do a matrice, go for it. Otherwise, it does sound awful. So, because if you take that,
Start writing out all the X,
Yep.
Y, and Z,
Yep.
you're not actually how it's done.
no, yeah. So, but I wanted to prove to you that what happens in your second and third deprotonation do not contribute significantly to, and also to remind you that you can only have one equilibrium concentration. So all three reactions have to have that concentration for H plus. Okay, you can't have three different concentrations of H plus in one beaker. There can only be one concentration of it, okay? And then you could go and calculate the pH, but I won't do that to you because I see brain is starting to leak out of Jerems's head. So that's when I know when to stop, when gray matter starts to leak out. So the homework, you're gonna read about polyprotic acids. Polyprotic, 681 to 686. And then gotta be, polyprotic problems. Say that fast. Numbers 105, 107, 109, 111. That's it. If you want to read the section on bases, you can.
Similar to this, but we call it.
Correct. That's why if you want to read, if you have some time and you want to read pages 675 to 680, go for it. Okay. Eventually you're going to read those pages. So if you have time, go for it. Otherwise, that's fine. You got 4 problems. All right. Oh yes, I can post today's class on YouTube. So, and if you are so interested, all the lectures for 14, 15, and 16 and 17 are all online. So you could binge watch them this weekend. We're not going to go further than chapter 14, but if you want to watch 15, 16, and 17, you can do it over spring break. All right. 15 and 16 are still equilibrium problems. It's just, just variations on a theme. All right. Any questions at home?
No, it's like searing pain.
I will upload today's class, but I probably won't be able to get to it until the end of the day. Okay.
My ear. Oh, no, reflex.